Hello everyone. So last time we stopped at this slide and we also learned about trans esterification, right? So one ester forms another ester with a different alcohol. So we will see how aspirin reduces fever and pain, and that we can incorporate some of the chemistry that we have learned, some of the reactions, and how we can get rid of the pain by having aspirin. Okay. So this anti-inflammatory and fever-reducing activity of aspirin is due to a trans-esterification reaction that blocks the synthesis of prostaglandins and the related thromboxanes. So these are biological molecules. Prostaglandins have several different physiological functions. One is to stimulate inflammation, and another to induce fever. Okay, so this prostaglandin synthase is composed of two enzymes, one of them cyclooxygenase. So cyclooxygenase has this CH2OH group. What is it? CH2OH, which is an alcohol, and in fact this is serine hydroxyl group. Serine is an amino acid. Okay, it has this alcohol group. So this is at its active site, and that is necessary for the enzymatic activity. Okay, when this CH2OH group reacts with aspirin in a trans-esterification reaction, the enzyme is inactivated. Okay, enzyme is going to inactivate. How does it going to happen? The oxygen, the basic form of the aspirin, going to take the proton from the alcohol, serine hydroxyl group. Now then this act as a methoxide group, CH2O minus. Now this going to react with the carbonyl group of the ester. Do you see, this is the ester part, and then it breaks the carbon oxygen double bond and it reforms the pi bond and leaves this group. Now what happened? Hydroxyl group is now acylated. Okay, so now this group is no longer there. The hydrogen is no longer there. Now the trans-esterification taken place. Now you have an acetylated cyclooxygenase, which is going to be inactive enzyme. Okay, so that is how aspirin works to get rid of the pain and inflammation. So you can see how the trans-esterification works in nature to help you out with aspirin. Okay, so this is a carboxylic acid, and in fact this one is acetic acid. If you look at the relative reactivities towards nucleophilic acid substitution, relative reactivities towards nucleophilic acid substitution. So most reactive is going to be carboxylic acid, right? Carboxylic acid, true. Carboxylic acid, and then you have the amide, and then once the hydrogen lost, you have a carboxylate anion. This would be least reactive. Okay, carboxylic acids can undergo nucleophilic acid substitution reactions only when they are in the acidic form, which is this form. Once it forms the basic form, carboxylate anion, now this is least reactive. This does not want to react with another nucleophile. Okay, this is also in the basic form. Carboxylate ions do not react with nucleophiles. How do you form the carboxylate ion? By removing the acidic hydrogen of the carboxylic acid. This is not going to happen. Reaction of a carboxylic acid with an alcohol. So we have carboxylic acid, we add excess alcohol. What's going to happen? We can form an ester. We call this process as a Fischer esterification. Excess alcohol drives the reaction to the right. So you can add more of alcohol, otherwise this is a reversible reaction. The more reactants you have, what's going to happen? You're going to be forming more products. According to the Le Chatelier's principle, when you add a reagent to the reactant side or the product side, it will move such a way to get rid of that reactant and to make the equilibrium again back to the equilibrium state. So by adding more reactant, it will go forward. Okay. And reaction of a carboxylic acid with an amine, carboxylic acid with amine, you can form ammonium carboxylate salt. That's what you're going to be forming first. A carboxylic acid is an acid and amine is a base. So acid-base reaction occurs. Always the first thing going to happen is the acid-base reaction. So now this is the base. So the nitrogen has a lone pair. So the nitrogen goes and take this hydrogen. So nitrogen will be positively charged with 4 bonds on it. So it already had 2 and 1. Now with the added hydrogen 4, it will be positively charged, and then the oxygen will be negatively charged. Acid-base reaction takes place first. And then when you heat it to a higher temperature, to 25 degrees Celsius, so then the reaction form the amide. So here's an amide and this is acetamide. Carbon, oxygen, nitrogen, NH2, CH3 group, acetamide. Amides, you know, they are least reactive. They do not undergo nucleophilic acid substitution reactions because the carbon-nitrogen bond is strong. So this is more basic. Chloride is less basic. So chloride will not be able to substitute for the amine group. So there's no reaction. Even with methanol. So because with methanol it's going to be making ester, but the amide is more stable compared to an ester, so no reaction. And then even with water it's going to form carboxylic acid. Carboxylic acid derivatives are more reactive compared to amide. So amide is more stable. So water will not be able to hydrolyze this one. Amides do react with water and alcohol if an acid catalyst is present. So these examples are without a catalyst, but with a catalyst we can make it happen. So this is an amide with water in the presence of acid catalyst. It can give you a hydrolysis of the amide to the carboxylic acid. With an alcohol in the presence of acid catalyst, we can make amide to an ester. Okay. This is the mechanism for the acid catalyzed hydrolysis of an amide. Again, we are doing the reaction in the acidic medium. Now you know what's going to happen if we are doing something in the acidic medium that has a carbonyl oxygen. So what's going to happen? So the carbonyl oxygen will first protonate. Okay. And then the water, if you are going to do a hydrolysis with water, neutral water molecule will come and form the tetrahedral intermediate. Okay. And then the water still having the hydrogen, the base will remove the excess hydrogen and we have a neutral molecule. Okay. So once you get to the tetrahedral intermediate, you have 2 oxygens and the nitrogen. Any of these, even oxygen or nitrogen, can be protonated. If oxygen gets protonated, we are going back to the starting material. But what we want is we want to move forward. So we're going to go ahead and protonate what we want to lose, which is the amine group. Okay, NH2OH can be protonated, but we protonate amine group. So now we have ammonia. NH2, as NH2, if it is going to lose, that's a strong base. But ammonia, NH3, is a weaker base. Now the protonated nitrogen, leaving a small stable molecule, ammonia, will propel the reaction forward. Weaker base is eliminated. And you will have this intermediate. So the ammonia, being a base, will go ahead and get that hydrogen on oxygen and create the carboxylic acid. Okay. Why hydrolysis and alcoholysis of an amide require a catalyst? Now here, once the amine group is protonated, the leaving group in acid catalyzed amide hydrolysis is the protonated ammonia molecule. Now if this is the uncatalyzed intermediate, the leaving group in successively uncatalyzed amide hydrolysis is going to be OH group. Now amino group, this amino group is a stronger base than hydroxide ion. It's a pretty strong base, amide group. So between these two, if you do the reaction without catalyzing, hydroxide will eliminate and we will get back the starting amide. In the presence of the acid catalyst, protonated amino group is a weaker base than the hydroxide ion. So the ammonia will lose. Okay, another drug, a penicillin. We all know about penicillin, how penicillin works. So we can also look at the mechanism of how penicillin works with the chemistry that we had learned. Okay, so antibiotic activity of penicillin result from its ability to acylate. Okay, and putting a carbonyl group, put an acyl group on CH2OH group of an enzyme that has a role in the synthesis of bacterial cell walls. So this is the enzyme that has a role in the synthesizing the bacterial cell wall. How does acylation occurs? So this is how the acylation occurs. Acylation occurs by a nucleophilic acyl substitution reaction. Okay, nucleophilics, the alcohol group OH adds on to the carbonyl carbon. So this is the penicillin. We call this as the beta-lactam ring. It needs to have this ring in order for this to happen. Okay, it reacts with the carbonyl carbon, forms a tetrahedral intermediate, and when the carbon oxygen pi bond reform, you can see here this is a four-membered ring. Oh, that's what's the word I was looking for. This is a four-membered ring. Four-membered rings are highly strained. So what happens is when the pi bond is being formed, the bond between nitrogen and carbon. So this is like an amide group. So normally this is called the beta-lactam. Lactam is a cyclic amide. Okay, so the carbon-nitrogen bond breaks. And then the nitrogen grabs a hydrogen. So once the bond is being formed, now the alcohol is acylated. You see that? We form an ester over here. So the enzyme action is no longer there now. Okay, so the four-membered ring amide is more reactive than a non-cyclic amide because then the pi bond reforms. The strain in the four-membered ring is released when the amino group is eliminated. Okay, so that is the driving force. So what happened is this acylation inactivates the enzyme and actively growing bacteria die because they are now unable to synthesize functional cell walls. And this penicillin has no effect on mammalian cells because they are not enclosed by cell walls. Okay, and also penicillin is supposed to store at cold temperatures to minimize the hydrolysis of the beta-lactam. Bacteria, and you also have heard that there are some penicillin resistant bacteria. Okay, so the bacteria that are resistant to penicillin, they secrete penicillinase, an enzyme that catalyzes hydrolysis of the beta-lactam of penicillin. So this is the beta-lactam. So those bacteria, they break down the beta-lactam ring. Okay, so the ring opened product has no antibacterial activity. So we want the penicillin with the ring enclosed like that so that this acylation can take place. Penicillinase destroys. So this is how the penicillinase, some penicillin resistant bacteria destroy penicillin. So this is penicillin. penicillinase. They opened up this ring and then opened. Penicillin does not have any effect on bacterial cell wall. Penicillinoic acid. These are some of the varieties of penicillins. So maybe around more than 10 different penicillins are currently in clinical use. You can see they differ only in the group. Alkyl group attached to the carbonyl group. Okay, that's it. That's about it. Don't need to talk too much about it, okay? Okay, so amide hydrolysis can be promoted by hydroxide ion. Now this is an amide group. Hydroxide ion. Hydroxide group goes and attacks the carbonyl carbon, opens up the pi bond, and then it can reform the pi bond and then eliminate NH2, but it will not eliminate NH2, and later on it will grab a proton. Okay, so we have the mechanism in the next slide. Let's go over that. Okay, the mechanism for hydroxide ion promoted hydrolysis of an amide group. Now this is happening in the basic medium. Hydroxide attacks the carbonyl carbon. You know this process already now, right? So then carbon oxygen pi bond breaks. Since this is happening in the basic medium, hydroxide will grab the acidic hydrogen from the other OH group, and now you have two oxygens negatively charged. Okay, and if the base does not deprotonate this hydrogen, what's going to happen? NH2 is a stronger base compared to OH minus. So then when the pi bond is broken, OH will eliminate. Just to prevent that, the hydroxide will grab this hydrogen. Okay, and it helps for the process. So the oxide, one of these oxides, can reform the pi bond and eliminate NH2. So since we are in a basic medium, we can eliminate NH2 minus. As soon as NH2 minus forms the base in the presence of the water, it can grab a proton and form ammonia and hydroxide. Okay. Gabriel synthesis we'll talk about in the next session.